work is exactly force multiplied by the distance against that force. So some easy examples following. A 6-pound book is lifted vertically 2 feet. How much work was done? Well, the force is the 6 pounds the book weighs, and the distance is the 2 feet. And so the amount of work that was done to lift that book 2 feet up was 12 foot-pounds. Yes, that is a unit of measurement, a foot-pound. Foot times a pound. There's no other good name for it. Foot-pound. I think, I don't actually know. I feel like horsepower might measure work. I'm not actually sure though. I don't know. It might measure private power. Or for example, a 10-kilogram chair is lifted up 2 stories, a distance of, I don't say 30 meters. 30? Sure, 30. So the work done is the force times the distance. A 10-kilogram chair has a force of 10 kilograms times 9.81 meters per second squared times the distance it traveled was 30 meters. So this here, right, if you're multiplying kilograms by gravity, you're getting what? Well, that is mass times acceleration, which is another name for force. But what's the unit of measurement of force in the metric system? Newtons. So we're getting 300, let's see, 10, so we're getting 98.1 times 30, which is a number I didn't count on having to calculate. So what? 327, 3,000. So it's a number. Guess I could actually calculate it. We could be precise here for a moment. I'm glad I filled out the attendance forms if you didn't already. Let's see, we get 2,943 Newton meters. Also known as a joule. Yes, 1 Newton times 1 meter is called a joule. A foot times a pound is a foot-pound. Right. Right, exactly. That's exactly correct. Because in the second example, in the metric system, our usual way of measuring something is by measuring how much mass it has in kilograms. So when we talk about mass, right, kilograms is a measure of mass. And if you want to say to get your weight in the metric system, even though you might say you weigh 50 kilograms, you'd be a liar because your mass is 50 kilograms and your weight is 50 kilograms times 9.81 meters per second squared. So your weight in the metric system, even though no one ever says this, your weight in the metric system would actually be, 500 Newton, 500 joules, yeah, or sorry, newtons, right? You would so newtons is the measure of weight in the metric system, but no one ever says they weigh 500 newtons. Someone would say I weigh 50 kilograms because on Earth, the gravitational constant is a constant, right? It's not like it varies slightly at different elevations, but essentially pretty constant. So on Earth, we just do that conversion, right? We're like, well, 50 kilograms is always the same weight. Whereas on another planet, your mass of 50 kilograms is going to weigh something different. Mass is a thing that doesn't change. Whereas, Patrick, you there you go. Cool. On the other hand, pounds is definitely a measurement of weight. It is a measurement of force. And the mass unit in the US system is terrible. It's called slugs. Yes, a slug is a measurement of mass in the US system, and a pound is a measurement of weight or force in the US system. So when I think about these kinds of things, weight is the same as force. When I'm thinking about how much force something is having, think about how much weight it has. I keep the like weight and force in my head are the same kind of thing. Whereas mass is, well, really force is your mass times your acceleration. Often due to gravity, not always due to gravity. Sometimes you have other accelerations. Yeah. So yes. So when you see problems like this, if you're asked to find the amount of work, if they're giving you things in the metric system and they give you kilograms, you do have to multiply by 9.81 meters per second squared. Or 9.8, 9.81. I don't remember. I think it's 9.8 actually. I think whatever. Whereas if you're in the US system, you're typically going to be given the weight in terms of pounds, and so you don't have to multiply by gravity because it's already been done for you. Yeah, kind of annoying, but it is what it is. And actually, and then yeah. So let's talk about springs. Not like the watery ones, like the ones that, you know, like a slinky kind of with a spring. So if you've ever stretched a spring, you might have noticed, depending, I mean, some springs are like, it gets harder to stretch as you stretch it further and further and further. Because there's some sort of kind of internal, I don't know, structure to the spring that makes it have like, you know, as you pull it further apart, it's going to be like resisting you more. And so what we're going to have here is that the force required to stretch a spring is proportional to the distance stretched. There are some caveats here. Namely, if you stretch it too far, you might kind of break the structure of the spring. So this is true for short amounts of stretching. If you stretch things too far, it falls apart. And this is what's called Hooke's law, that the force is equal to a constant times x, where x is how far it's being stretched. Distance stretched. And for F is the force required. And K is the spring constant, which varies depending on what your spring is. Some springs have larger spring constants, some springs have smaller ones. And this is called Hooke's law. So for example, excuse me, if a 30 Newton, sorry, if 30 Newtons, yeah, phrasing for you. If 30 Newtons of force is required to stretch a spring from its natural length of 5 meters to 6.5 meters, what is the spring constant K? Well, that's easy enough. We just throw things into this formula. So the force required was 30 Newtons. And it's equal to the spring constant K times the distance stretched, which was how much? Well, right. So 30 divided by 1.5 is going to be 20. And it is, we don't really care about the units that go with the spring constant, but it's notable, I suppose, that it is newtons per meter. That's our spring constant. Okay, seems all right. Yeah.
Asked me something that was like dy of dt is equal to k times y. Is that like what this is, or is that something else?
No, that's something completely different.
Okay.
That's like exponential growth. in decay.
Yeah.
Yeah, that's a totally different
Okay.
thing. So. Second question, which is more interesting. How much work was done? When we stretched the spring? From 5 meters to 6.5 meters. So here's what's important to know. We can't just say the work was the force times the distance, because the force varies as we start, right? As you pull the spring further and further, it requires more force each time to pull a little bit further. So we can't say that the work is going to be, interesting note here, one second. Oh, sure, yeah, okay. We can't say that the work is going to be just this 30 newtons of force times the 1.5 meters is being stretched. Because, you can see this, right? Yeah, let me do this a little bit here. Because, oh, let me give you guys, sorry, just in case you didn't get it yet. Force changes as the spring stretches. You need to use an integral. So when I think of these spring type problems, I usually draw a picture kind of like this. I've got my spring, and then well, a little bit more. Right. So here's my spring, and here's like its natural length of 5 meters. And here's it being stretched out to a total length of 6.5 meters. But really, when I do this, what I'm thinking of is this here being x equal to 0 is how much it's been stretched. And over here, this is going to be x equal to 1.5. So really, I care about measuring not how long the spring actually is, but how far it's been stretched from its natural length. And so the idea here is that to say, move it from this little spot here to this little spot here, well, we're going to say the following. Consider a small length of the spring. A distance x from the natural length. Then here's the important part. The work done in stretching from x to x plus a little more, we're just stretching it a tiny little bit, well, it's going to be the force times the distance. Over this little tiny bit, it's essentially the force is constant, right? If you're just changing how far the spring is stretched a very, very, very small bit, the force doesn't really change that much. So we're going to say it's going to be the force times the distance, which in this case is, well, the force that's holding the spring is, according to Hooke's law, K times X, right? That's what the force is, Hooke's law. I know we're kind of we're taking Hooke's law to be true. No one's verifying it for us. It's just we're saying it's all true. But that's our force, and our distance is a small change in X, the dx. There's our force, there's our distance. That's the work done, moving the spring, stretching the spring from here to there. But then we want to stretch the spring all the way from here to there. So what are we going to do? We're going to integrate. Bless you. So the total work, oh, and in this particular problem, our K was 20, which I know I pointed to and you can't see, right? But it's still 20 from before. So that's going to be 20 times X times dx. That's the work done over just this little distance here. So then the total work is going to be the integral from x equals 0 to x equals 1.5 of 20x dx. I will point out, because it's nice, so it's nice to do some dimensional analysis sometimes with these problems to think of what the units actually look like. Just to point out, this is newtons per meter times meters times a small change in x, which is going to be meters. So we've got Newton meters, which is a measure of work. Which makes sense. Really, we kind of ignore that and be like, oh, we're going to add a new dimension, we integrate, but same kind of idea. So what we're going to get here is 20x squared over 2 from 0 to 1.5, which is going to be 10 times 1.5 squared, which is something. 2.25 times 10, so 22.5. And a Newton meter is a joule. So it took 22.5 joules of work to stretch this spring from a length of 5 meters to a length of 6.5 meters. Questions? Yeah. So here's the way I think about it. I've got really what I'm integrating here is I'm integrating newtons with respect to x. Right, because the dx there is its own little thing, right? So basically, I'm integrating with respect to x, and x is representing a length, right? So essentially, I'm integrating this, and I'm getting newtons times meters, the dimension of the variable that I'm integrating with respect to. It's kind of similar to how when if you were to integrate, say, if someone said my velocity was, 10 meters per second on the interval from 0 to 5. I'm making it super simple just to show you, right? You could certainly say that from 0 to 5 seconds. So I could say for sure, if I travel at 10 meters per second for 5 seconds, I'm going to travel 50 meters, right? But you could also do this with an integral. You could say, oh, well, my distance traveled is going to be the integral from 0 to 5 of my velocity. And when you integrate with respect to time, you essentially multiply by a unit of time. So you end up getting 10 meters per second times seconds, and you're evaluating, 10 t from 0 to 5. And you plug in the 5 and you plug in the 0, and you get 50 minus 0, which is 50 meters. So really, when you're integrating with respect to a variable, you're kind of multiplying by the unit that variable is measured in. And when you're differentiating with respect to a variable, you're kind of dividing by the unit that variable is measured in. So like if you differentiate velocity measured in meters per second, what's the derivative of velocity? That's the antiderivative, acceleration, right? It's meters per second, or meters per second squared. So that's kind of the idea. I always think about this as when you differentiate, you kind of divide by your variable. And when you anti-differentiate, you kind of multiply by your unit or your variable. Good? Cool. Yeah, it usually works out pretty well. What if, on the other hand, what if we stretch the spring from 6.5 meters to 8 meters? Another 1.5 meters. Is it going to take another 22.5 joules of work? No, right? Because it takes more force to stretch it further and further out from its natural length, and work is force times distance. So if the force is greater to stretch it longer, it should require more work to stretch it longer. So luckily, the process is still very much the same. We're just going to do the integral from, instead of 0 to 1.5, I guess I would still draw my picture. Right, so I'm going from 6.5 to 8. I'm also marking 5 because 5 meters is my natural length. So this is my natural length where x equals 0. This is my stretched out to x equals 1.5. This is my stretched out to x equals 3. I'm going to be integrating from 1.5 to 3 of the same function, 20x dx, which is not too terrible. I mean, right, it's going to be 10x squared from 1.5 to 3. You're going to get 10 times 3 squared minus 1.5 squared, which is going to be 10 times 9 minus 2.25, which is 10 times 6.75, which is 67.5 joules. And capital J is for joule. It totally changed. I anti-differentiated. Why is it the same here and here?
Yeah.
Because regardless of where we're doing it, if we're thinking about just moving it a little distance, right? The work done moving it that little distance is the force, which is 20x according to Hooke's law, times the distance, which is your dx. So this is your force, Hooke's law, this is your distance.
Since there's a variable, like you can just say 20x. Yeah.
Yeah, if we're talking about not newtons per meter, newtons times meters is joules. Yeah. Force, yeah. So work in the metric system is measured in joules, newtons times meters, which is joules, and in the US system is unfortunately the lovely name foot pounds, feet times pounds. So yeah, here, same deal. Force times distance. But there are other situations where other things like not a hook, where the force is not going to be measured as, some constant times x. In fact, like in our next example. Question.
Why think the natural state that's the given for the first time?
Correct. Yeah. The other variety of this question, which I'll have to remind myself here, is so in this problem, we were told that the amount of force required to hold the spring at a certain length was something. And then we were able to find the constant K because of that. Here is a variation on the spring problem that might look similar, but is a little bit harder. So let's say, I'm just gonna make up numbers and hope they come out right. 20 joules of work is required to stretch a spring from its natural length of 80 centimeters to a length of 110 centimeters. How much more work is required to stretch it from 110 to 130? Okay, so first things first, we stretch it 30 centimeters. We're not going to be saying that 20 is equal to 30 times x or 30 times k, because that would be true if we were told how much force, not work, was required to hold it at a certain length. We were told how much work was required to stretch it to that length. So here's what we've been given. We've been given a problem. So I've got my spring, its natural length is 0.8 meters. And yeah, we want to measure things in meters, not centimeters. So if you're given centimeters, we usually want to change it to meters. And that's the natural length. So you've done 0 stretching there. And then this further length of 1.1 meter, 110 centimeters, means we've stretched it 30 centimeters or 0.3 meters. So here's what we know. We know that the work done to stretch from here to here, which would be the integral from 0 to 0.3 of Hooke's constant times x dx, right? It's still the same thing, right? This is still your force. This is still your distance. We were told that that's equal to 20 joules. We can use that given information to then solve for K. If we integrate this, we get kx squared over 2 from 0 to 0.3. I should have picked a different number. 0.8 is going to be terrible. Oh well, equal to 20. And we can solve for K. So we're going to have K times 0.3 squared divided by 2 equals 20. So K is going to equal 40 over 0.09. Which I immediately regret, but such is life. So, just want to point this out again. If you're given, like in our first problem, if we were given, it takes 30 newtons of force to stretch a spring or it really should be to hold a spring from its natural length of whatever to whatever. If instead you're given how much work is required to stretch it to that length, you have a different given. And it's a little more complicated. Because work is always going to be the integral, force is just this K times x. So now we can answer the other question. We want to stretch it further to a length of 1.3 meters, which is going to be integrating it from 0.3 to 0.5. Because that's how far we are beyond the original. So to calculate the work asked in this question, it's going to be the integral from 0.3 to 0.5 of our K value, 40 over 0.09. 4 choices were made, x dx. And I think I'll leave it there because I know you all can do that integral, right? You're just going to get x squared over 2, and you're going to, I can write one more step. It's going to be 40 over 0.09 times x squared over 2 evaluated between 0.3 and 0.5, which is terrible, but not that terrible in the grand scheme of things. Yeah.
So once we get like the constant, it doesn't matter if we're going from like 0.5 or 1 to the.
Right. You just have to know where you're starting and where you're ending. Yeah, the constant is the constant is the constant. Never changes once you know it.
For these problems, like from 0.3 to 0.5, that's the work just for that bit, right?
Right. Just to stretch it from a length of 1.1 meters or 110 centimeters to a length of 130 centimeters. Yeah, exactly. Well, wait, the full, what do you mean by the full amount of force? So the thing is, you can't really go from 0 because we want to go from the natural length of the spring, which is 0.8. So if I said how much work was required to say stretch it from 0.8 to 1.3 meters, you could do the integral from 0.8 to 1.3. Oh, sorry. Not really that, not what I just said, not from 0.8 to 1.3, but from 0 to 1 to 0.5. But you could also just say it's going to be from 0 to 0.3 plus from 0.3 to 0.5. So you could take the 20 joules that it took to stretch from here to here and add on the however many joules this is to get from there to there.
From like 0 or 0.8 to 1.3.
Well, so that would be like you were stretching it from 1.6 to 2.1, because right, what these are the numbers that are your limits of integration. The how far beyond the natural length we have stretched it. So if you want to stretch it from from its natural length of 0.8 meters to a length of 1.3 meters, that's going to be the integral from 0, because you stretched it 0 if you're at 0.8, to 0.5, because you stretch it 0.5 if you're stretching it to a length of 1.3 meters. Yeah, it works for compressing. I just visualizing the compressing always feels weird to me, so I always present it in this way. But yeah, it works for compressing as well. No, it's still a positive amount of work. You just have to kind of reframe your frame of reference. let's look at another different example. So work in general, force times distance. If there's one thing to take away from what we said today, is that one fact. Work equals force times distance. Or if you prefer, work equals weight times distance, right? Force is just weight, weight is just force. At least that's the way it works in my head. So let's look at this example. A 50-foot cable, not a spring, a cable weighing 100 pounds is used to pull an elevator weighing 1,000 pounds. How much work is, I like to say, is done, but you can also say required, is done when pulling both the cable and the elevator the entire length of the cable, the entire 50 feet. One of these parts is really easy to do. The elevator is 1,000 pounds no matter how high up it is. So the first part here, the elevator is easy. The work is going to be the force or the weight, which is 1,000 pounds, which is the measure of force, times the distance it's going to travel, which is going to be the entire 50 feet. And so we're going to get 50,000 foot-pounds. I do like saying foot-pounds. It's fun to say. It's a foot-pounds. Okay. Anyway, on the other hand, the cable is more challenging because you're not moving the entire 50 feet of cable 50 feet. Right? The top part of the cable hardly moves at all. Right? It gets sucked up and then you're not like doing work to pull it up because it's like in the windy part or whatever. We're pretending like we don't do pull, whatever. We're ignoring that. We just said to pull up, not to deal with it afterwards. So it's good to draw a picture. And this is where people really kind of vary on how they like to set up their frame of reference. So I personally tend to be a big proponent of the bottom is 0 and the top is positive. Or maybe the top is 0 and the bottom is negative. But as you move from lower to higher, you are increasing your height. That is my personal preferred way of always doing it. But not everyone does it that way. So I'm going to show you this next part kind of in 2 different ways, just so everyone can kind of see their ways of doing it. So what we're going to do is we're going to think about how if we look at some length of cable X, and that length of cable is going to move a short distance dx. So I guess maybe it was here and then it moved up there. Oh, yeah, that's why I really don't love this. And that's why I'm doing it the way I don't like doing it first. And to me, it feels super backwards. So here's what we've got. The cable gets lighter as it shortens because there's less of it. So the weight, aka the force, varies. So here's one way we can look at it. When there are X feet of cable out, right? So we've pulled the elevator up to this spot and there's still X amount of cable out. The work needed to move it dx feet, well, force times distance. How much does this cable weigh? It's not the whole cable, so it doesn't weigh all 100 pounds. There is an assumption being made, which is usually true, is that it's a cable of constant density. Meaning this 100 pounds of weight over 50 feet of cable means that the cable is 200 pounds of weight over 100 pounds of weight over 50 feet, or 2 pounds per foot. The cable has a density of 2 pounds for every foot. And so if we want to move it dx feet, well, we've got x feet of cable. So the force is going to be, well, I've got my x feet of cable times 2 pounds per foot. So it's going to be 2x pounds per feet times feet. Pounds. It looks like a times, it's supposed to be an x. I gave myself too much room there, sorry. Pounds per feet, and that's in feet. So you get pounds. And then we're going to multiply that by distance, which is going to be the dx. That's how much work it takes to move it when it's x long, a short distance dx. And then, if we do this, what I think it was the backwards way, if we think of this being, well, here it makes sense for x to be 0 because we're thinking about how far it has to move, right? Up here, when we've gotten to the top, there's 0 feet of cable to move, whereas down here at the bottom, there are 50 feet of cable to move. So we're going to integrate this from 0 to 50 of 2x dx. And we're going to get x squared from 0 to 50, which is going to be 50 squared, which is 2,500 foot-pounds. So then the total work done, right, so this is the work of the elevator, this is the work for the cable, and the total work, we just add them together, and we're going to get 50,000 plus 2,500, which is going to be 52,500 foot-pounds. Question?
So you're saying that the density is 2
Pounds per foot. Correct.
If we have the density, isn't force mass times distance? So
Force it, no, well, force is mass times acceleration.
acceleration. So we are getting, why are you using density? I'm a little confused.
Because I'm only using density so that I know how much this length of the cable weighs.
It's gonna be the-
Let me put it to you another way. How much cable is there in total? Right, how much of it do I have? Right, so I have this fraction of the cable, right? And if I multiply that fraction of the cable by how much the total cable weighs, I get 2 pounds per foot.
That's the weight of whatever, however.
That's the weight of 1 foot of cable. Well, no, well, this is the weight of x feet of cable. So this 2x is how much x feet of cable weighs. Okay. You're welcome. Okay, just so I have a hard, as you might have noticed, you might not have, I struggled a little bit with that. It was hard for me to kind of imagine thinking of x as how far away we are from the thing. So I just want to point out, you can do this other part in a slightly different way. Your professor might not cover it at all. They might do it this way we just did it, or they might do it in this other way. So let me just show you. You don't need to write this down if you don't want to, but let me show you how I might do it instead. So, and I'm just doing the cable part because we've already dealt with the elevator part. And I'm going to use y's instead of x's just to show, to make it different. So I'm thinking of this as being a height of y equals 0. I'm on the ground floor. And this is going to be a height of y equals 50. I'm at the top. And what I'm asking here is, okay, if I always have to think about this very, very carefully. Yeah, I really do imagine this differently. Sorry, the problem with these work problems is you can kind of sometimes imagine the distance as the dx, and sometimes you can imagine the force as the dx. And what I'm actually going to do, I'll show you because it's worthwhile, is I'm actually thinking of this little segment here, I'm thinking of that as being at a height of y. It has a thickness, or sorry, a length of dy. And this part here, this little section that's dy long, this section, which I know looks weird the way I've drawn this, but fine. This weighs dy times 2 pounds per foot. I should say dy feet times 2 pounds per foot.
So is it because you're doing it in terms of y, it's now 50 to 0?
I'm literally only using a different variable just to make sure that it looks different, but I could have just as easily said x. X would have been totally fine to use. I just wanted to make it different. People often use y though when they're going vertical.
Yeah.
Okay, so now this little section weighs 2 dy pounds. That's it, weighs 2, right? That's the force or the weight of this little section. What distance does that little section have to travel to get to the top? Well, it's already at a height of y. How much distance is left to go? 50 minus y. So here, when I'm thinking about my work of my little strip, my work is going to be my force, 2 dy, times my distance, 50 minus y. Yeah, I really can't. The other way is just weird to me. Fine. So then I'm going to add up all the works. So I'm going to take, how much work does this strip? Well, that's going to be when y equals 0 and it had to travel 50 feet. And how much work does this little strip have to do? Well, it's going to be when y equals maybe like 45 and it's going to travel 5 feet. So I'm going to, once again, to get the work, add up all of the things, right? When I say add up, you should know I mean an interval, right? We are adding up. We are adding up all the little infinitesimal slices or strips or whatever's from as low as y equals 0 to as high as y equals 50. 2 times 50 minus y is dy. If we do this, we get the same answer. We do the integral from 0 to 50 of 100 minus 2y dy. We get 100y minus y squared from 0 to 50. We end up getting 100 times 50 minus, oops, no, that's fine, minus 50 squared, which is exactly 5,000 minus 2,500, which is also 2,500 foot-pounds, the same as before. And to me personally, it's a matter of preference. Some people have an easier time thinking of this length as the distance we have to travel, and this little part here as how much the thing weighs. Some people have a much easier time of thinking of this length has some weight to it, and it's going to travel a small distance dx. There are some problems where it's easier to do it this way. There are some problems where it's easier to do it this way. And it really kind of just depends. Question? Uh-huh.
Every time you're adding all the distance we have and all this.
Well, the thing is, it works either way. So here I'm thinking of the distance as how long this section here that has some constant weight to it is going to move.
You're saying that what it takes to move any section all the way to the top and adding up all the.
Right, exactly. Okay, what time is it? 1:51. All right. So the problem with this work stuff is there's so many different ways to count. There's so many different works to talk about. So you can do works like this. We'll come back to another example like this next time, I feel like, because I want to kind of do another example of a different style, which is the following. So you can there's a lot of like work lifting a thing, and it's often like some mass at the bottom, which just is whatever that weight is times the distance to travel, and then the cable or the rope or the whatever, where you have to do that kind of thing. See, sometimes somebody gives you a leaky bucket style of problem, which has an added issue where you have water leaking out, and then you have to calculate how much work is done for that water as well, and the weight of it's changing as you go up. We'll talk about that next time, because it's definitely, it's a challenging thing. But let's look at another style of work problem, which is pumping fluids out of tanks. When we think about it, it does make some sense in the context of work, in that you're going to be moving a bunch of water, which has some weight, some distance. So you're going to have a weight times a distance, which will be equal to some work. Seem okay? Okay. So let's look at the following. Ooh, I'm starting off with a tough one already. So find the work required to pump water, which people usually say has a weight density in the US system of either 62.4 or 62.5 pounds per cubic foot. I forget what it is in newtons per cubic meter, but I feel like it's something nice, like 1,000 newtons per cubic meter or something very straightforward. The US system, the number is always wacky. And then we want to pump this out of a container that is a 6-foot radius hemisphere bowl, right? So like, you know which way you would make the hemisphere if you wanted to hold water. Not like this, like this. Filled to a depth of 3 feet. So here's the situation. Here's my bowl, and it's filled. I should use blue. It's filled with water 3 feet deep. So you've got, right, this has a height of 6 feet. And this is the height of 3 feet. And we want to pump it out the top. So we basically just want to pump it to the top. Now, you might be asking, where's the water going to go after that? We don't care, right? You're just pumping it to the top and pretending it goes somewhere. So maybe you've got like a pump and it's going like right over the edge there, right? Like here's your tube with the pump attached over here. All right, like it's going like that and pumping out the water. Mm-hmm. Yeah, it's the height because this hemisphere, essentially, this is the center of the hemisphere, and here's the radius, which is equal to 6. Here's the radius, which is equal to 6, and so on and so on and so on. Okay, so for this kind of situation, we have to think about the fact that work equals force times distance. And since we want to think about the distance the water is moving, well, not all the water is going to travel the same distance. Right? The water at the very top is going to travel 3 feet. The water at the very bottom is going to travel 6 feet. The water in the middle is going to travel some other distance. So what we're going to do is we're going to take a slice of the water that is all at the same depth. So that we can think about how that slice of water is essentially all going to move the same distance. So we can calculate the force of it, or so the work for it, by seeing how much it weighs multiplied by how far it's going to go. Typically with these 3-dimensional shapes, usually it is to our benefit to draw them as a 2-dimensional projection. Meaning we're just going to take this hemisphere and instead draw it as a semicircle. That's right. So let's draw it like this instead. And yeah, there's so many ways to do this. So I'm thinking of, right, the water level, which is blue. I got do I have enough time? I might have enough time. It's gonna be tight. So here's my water level, right? And what we're gonna do is we're gonna take a slice that's all at the same depth. So here's my slice. It's all at the same depth. which is really a nice little, disc. And if I knew what the radius of that slice was, I could find the volume of this little disc. Okay, so a couple ways to do this. Again, we're going to do it the James way because that's the way I do it. Shocking, I know. James does it the James way. I'm going to say this is the bottom. This is y equals 0. This is the top. This is y equals 6. If you look at Grant's notes, he does orient things differently, which is totally fine. It's just different. And then what I'm going to do is I'm going to draw this little radius of the sphere right here. I know that's going to be 6. I'm going to think of this strip as being at a height of y. I'm going to let y vary from as low as 0 to as high as what? Not 6. It's a trick question. To as high as 3. Right? Because the water only goes up to y being 3 high. Okay, so let's find. So I really want to find the work for this slice. But to do that, I really need the force of the slice times, well, I know what the distance is going to be. If this slice is at a height of y, it's going to have to travel 6 minus 1. That's definitely the distance that this slice is going to travel. Okay, force is just weight. Weight is just volume times density. This is really going to equal the volume of my slice times the density, which you know is 62.5 times 6 minus y. Okay, volume of this slice. Well, it's a circle with some thickness. So this circle, the circle has a volume of, well, it's pi times whatever my radius is squared times my thickness, which is a small change in y. Radius squared, well, look, I've got a right triangle here. I can say that my radius squared plus 6 minus y squared is equal to 6 squared. And then my radius squared is equal to 6 squared minus 6 minus y squared. And I could solve for r, but I don't need to. Because I don't want r, I want r squared. And I've got r squared, well, great. What I should do, though, is I should simplify this because it does get nicer. This is equal to 36 minus 12y plus y squared, which ends up simplifying to just 12y minus y squared, which is a little bit nicer. So that's going to be what goes in for the radius squared. So the volume of my slice here is going to equal pi times 12y minus y squared dy. And that's what's going to go in here. So the work of this slice, the work to pump the slice out of the top of this hemisphere is gross. It is 12y minus y squared times 62.5 times 6 minus y. Times pi. Thanks. Good call. I often forget the pi.
You don't need a
What's-
y.
Times dy. So that's the work of just this slice. And then we're going to add up the work for all the slices that go as low as y equals 0 and as high as y equals 3. So the total work would be, I would probably pull out the 62.5 and the pi in front. And then we do the integral from 0 to 3 of 12y minus y squared times 6 minus y. We should stop there because it's 202. Question?
Yeah, so turn the force into volume.
Well, so what I said was, I said that force is equal to volume times density. Because the volume here is measured in cubic feet. And the density is measured in pounds per cubic foot. And so the cubic feet cancel and you get pounds, which is a measure of force. Yeah, that's what I did there. You're welcome. All right, we'll talk more about work on Friday and maybe some centers of mass moments and stuff like that.